Good afternoon. My name is Laura McDermott. I'm working with Kathy Heidenreich and Marvin Pritz and Dr. Harold Vaness on this soil management and berry crops grant, and I'm happy to have you here. I hope that there'll be a few other folks joining us here as we get going. I do want to, I think probably most of you have already um, taken the time to fill out the SARE demographics questionnaire and the educator pretest, which is in the file box on the lower right-hand corner of your screen. But if this is your first time visiting us for one of the webinars and you have not done it, please take a few moments, either right now or at the end of this presentation, to fill that out and send that to Kathy Heidenreich. It's very important for the grant. And while we're on that topic, I might also remind folks that we are in the final phase, the last 3 webinars, today, then March 2nd, and then the final one will be on March 9th. And at that time, we're going to have a post-test of all the educators. Hopefully, we're going to have a really good showing for that final webinar, because that's a very important consideration in how effective the webinars are for relaying educational information that extension folks can use out in the field with growers. We also want to remind those of you who have been in attendance for a number of these webinars that we are hopeful that you'll take the opportunity to make the next step. So using all of the materials that will be available to you as participants in this first portion of the grant, we'd like to have you take those educational materials out into the field and host some grower workshops, grower field days, whatever, and then kind of report back to us. And Kathy has some formats, and if you have any questions, you can contact her or myself about that. But we'd love you to start to get your head around that and plan for something this growing season. All right, before we get going, also I'd like to make sure folks know a little bit about the webinar. I think most of you have done this, but you can type into the chat box, the long narrow box at the bottom in the center. That's where you enter your comments and questions, and I will try to keep track of them. Please go ahead and introduce yourself if you haven't done that yet. Even though you may feel like you do it every single time, it's helpful for the presenter to kind of get to know where everyone's from. Additionally, the web links, which is in the lower left corner, you can click on that and then you can actually browse to that right now or at the end. We're going to go back to this kind of format at the very end. So they'll be there, and they'll also be accessible as the recorded webinar. All right, today, this is the 10th in a series of 12 berry crop nutrition and soil management training webinars. And our speaker today is Dr. Harold Vaness, who's the professor and chair of the Department of Crop and Soil Sciences at Cornell University. And I will now switch into that presentation mode. Dr. Vanessa's current research and extension interests are in precision management of nitrogen, soil health, and space and time statistics. He teaches an undergraduate course in soil management for sustainability and a graduate course in that space and time statistics. He has authored over 100 refereed publications and 4 books and advised 45 graduate students. And I'm exhausted for him, so I'm really glad that he's here. Hey, Harold.
Hello, can you hear me?
Sounds good.
Okay. Well, thank you, Laura, and it's a pleasure to be joining this group again. I looked at my my calendar, and it was almost exactly 4 months ago when I did the first webinar, one of the early ones on basic soil information and soil management principles. And since then, we've discussed, as a group at least, nutrient management and soil health management, and doing that mostly from a production perspective. Today, we're going to be talking more about some of the environmental impacts and how we can reduce that. Let's see, I'm having a little bit of a problem. There we go. Going to the next slide. Okay, the outline for today, and by the way, I just put my picture up there. It's a slightly different picture than the other one, just to make it a little bit more personal for you. But we'll start today with discussion of environmental loss processes, then erosion and runoff prevention. Then we'll talk about managing phosphorus, and then managing nitrogen. Do a summary, and then we'll go into the question and answer session. And I try to organize my slides and my presentation in a way I think that will allow you to take some concepts that you can use with your stakeholders that will help you, I think, in your educational programs. So we'll start looking at environmental losses. The primary ones that we might be concerned about with berry production is sediment, nitrogen, phosphorus, and pesticides. And I should say up front that most of the berry production is done in a way that is relatively sustainable, has relatively little environmental impact, say, compared to corn production, which is more large scale. It's an annual crop. A lot of these soils are being tilled on an annual basis. And so when we compare that to most berry crops, we're dealing with perennials and not as much tillage and typically not as much nutrient inputs either. So often the environmental impact may be smaller, yet we do need to be concerned about that, and we need to take that serious. So in the picture here, you see basically the basic hydrologic cycle, and the main point is that these environmental losses occur when we have a lot of water in the system. So that water, of course, comes mostly as precipitation, in some cases a little bit as irrigation. But really, it's the extreme precipitation events when we get an inch, 2, or even more. That's when we tend to have the problems. And so an important concept to consider is what happens at the precipitation when it reaches the land surface. And it can basically go in two directions. It can either infiltrate, or the water that does not infiltrate then runs off and creates all kinds of problems, because it will take with it these contaminants like sediment, nitrogen, and phosphorus. And if it takes sediment, then we refer to that as erosion. And that may readily, of course, reach streams or other water bodies like lakes and estuaries, and that is, in general, very undesirable. But if we're lucky, all the water infiltrates, and then it's being held in the soil. And I like to refer to the soil as a sponge, and the soil holds on to that water and then makes that available to the plants through evapotranspiration. If there's excess water in the soil, then it will percolate further down, either to deeper groundwater or maybe shallow groundwater that might eventually reach a stream. So those are the processes. And so if chemicals go with the percolating water, then we refer to that as leaching. So if we think about these loss pathways, the ones that we're concerned about are runoff, mostly with phosphorus, to a lesser extent with nitrogen, and then maybe with pesticides. For erosion, which means that runoff that takes with it all the sediments, and the sediment in turn may have a lot of phosphorus with it, or some nitrogen and pesticides. And so all of these contaminants are a concern when we have erosion. Erosion is a really bad thing. When we have leaching, we're concerned mostly with nitrates and pesticides. Phosphorus basically doesn't leach except in some very unusual circumstances. And then finally we have a concern about gaseous losses. And that is typically not directly driven by water, but indirectly, especially when it comes to nitrous oxide, which is generated when the soil becomes anaerobic. And so when it's saturated and there's no air in the soil, and then the nitrogen is transformed from, say, nitrate to nitrous oxide. And of course, this is a big concern because it's a serious greenhouse gas. It's 300 times more potent than carbon dioxide. And we may have some gaseous losses of pesticides, which is really unrelated to water typically. That has to do with the properties of the pesticide itself. And I'm not going to discuss pesticides in detail today. It's a little bit beyond the scope of what we wanted to talk about. So we're going to focus on sediment, nitrogen, and phosphorus. So the environmental loss potential in general is affected by a number of factors. So one, obviously, the weather, we discussed that. If you have a lot of intensive rainfall, you have higher potential for runoff and erosion, and excess water also generates leaching. Secondarily, we have these inherent soil properties like texture and organic matter, which also affect, basically where the water goes and what it takes with it. And then we'll discuss that in a little bit more detail. Thirdly, soil health. And we've talked about that. Bob Schindelbeck mentioned that in the previous webinars. So if we build up our soil and we make it healthy with, say, good aggregation, then we can reduce the environmental loss potential significantly. And then finally, perhaps what we might call the more real-time soil management practices, such as whether we cultivate the soil, which may expose it to the elements, whether we have soil cover like mulch, whether we traffic the soil causing compaction, and those kind of things. And then, of course, last and not least, is how much fertilizer we apply, either organic or inorganic fertilizer, and where we place it, because in principle, the more fertilizer or other organic materials that we put out there, the higher the potential that we have losses. So we'll come back to these individually. But first, let's discuss the basic inherent properties of soils and how that affects potential environmental impacts. The texture or the distribution of particle sizes in terms of sand, silt, and clay is probably the most fundamental property, and we're all familiar with the textural triangle. And it provides the basis for a lot of these environmental loss considerations. I like to talk to my students or to stakeholders as the soil particles and the texture of the soil sort of defining what we might call the house, the basic structure of the soil. And I like to use the analogy of a house in that you have the structure of the house, which is the walls and the roof and the basement and all that, and that's the most visible part of a house, and it particles for the soil. That's what you see. The most interesting part, however, is what happens in the spaces between the soil particles, or with the house analogy, what happens in the rooms, because that's where all the processes take place, that's where the organisms are, that's where the life is, and that's where the interesting things happen. So in soils, there's bacteria, fungi, all kinds of organisms that live in the pores, and that's also where all the important processes of water and air movement occur. So I'd like to have people, farmers and students, to think in terms of soil, not just in terms of the particles, but have them think in terms of the spaces between the particles. So when we think about a sandy soil, then most of those pores are relatively large. Although in general terms we're still talking about less than 2 millimeters in most cases, but by soil standards those are very large pores, and those pores will lose their water very quickly because the capillary force that we see in large pores is relatively weak. Conversely, when we talk about clay soils, we mostly have small pores. The capillary force is really, really strong, and they retain the water very tightly. Okay, but if we have a clay soil that actually has good aggregation, then we may have a few larger pores that are between the aggregates. So then we maybe have both small and large pores. So this is an example of an aggregate that has the range of pores. So it has the larger pores, and those facilitate infiltration and drainage, aeration, and rooting, because they lose the water very quickly because of the weak capillary force. The small pores, they retain the water very well, and so they facilitate both water and nutrient retention. So when we're concerned, for example, about leaching, we like to see these nutrients being retained in the soil. So I have a question for you here. Actually, two questions. First one is, which soil has a higher leaching potential? A sand, a silt, or a clay? And the second question is, which soil has a higher runoff and denitrification potential? The gaseous losses of nitrogen, the sand, the silt, or the clay? And I'm sure you all got this question just right. It's of course the sand that has the highest leaching potential because it's mostly large pores, doesn't retain the water and the nutrients very well, so they easily wash out with the percolating water. And for two, it's of course the clay that has a higher runoff potential, mostly small pores, so not very good infiltration capacity. And because it is mostly small pores, the aeration can often become a problem when you get a lot of water, and so you have higher denitrification. So I am sure you all got those answers correct. So when we go back to our textural triangle, again, so we're talking about the more sandy soils like a sand, a loamy sand, sandy loam, a lot of large pores, high leaching potential. When we have higher clay contents, we tend to have higher runoff and denitrification potential. Now let's look at things a little bit more in a landscape perspective. And we often use the term hydrologically sensitive areas for parts of the landscape that have a high potential for pollutant losses. And in some cases, we're concerned about runoff, surface losses. In other cases, it's leaching and subsurface recharge losses. So when where do we in the landscape have high runoff losses? In floodplains. And this is kind of an interesting scenario because most floodplains actually tend to have relatively coarse textured soils like gravels or kind of sandy soils that you might say, well, they have high infiltration capacity, but because they are located near a stream, basically if you get heavy rains and you get flooding, then basically everything goes. So you have not a lot of nutrients on the soil, or the soil is very poorly protected, then a lot of that gets lost. And in the Northeast, we certainly experienced that this year with a hurricane and a follow-up in parts of the Northeast with some other heavy rainfall events. So similarly, areas that are adjacent to flowing or standing water bodies are hydrologically sensitive primarily because they tend to be wetter areas in the landscape and because they are close to these water bodies. So there's very little buffer, very little opportunity to filter out some of these contaminants. Areas with low infiltration capacity are a concern, maybe because the soil has become compacted, or sometimes it's even when it's adjacent to, say, a road or some other compacted area where the runoff that comes off that area then goes onto a field and may reduce runoff and erosion on the field. And then areas generally that are saturated, that are already wet, have a high runoff potential as well. Okay, so let's then think about the leaching and subsurface recharge areas. The ones that we're mostly concerned about are areas that are close to either wells or springs. These are typically areas that have very permeable soils, and when you're very close to these water sources that people use for drinking water, we need to be extra careful. And so that's those are sensitive areas. And in general, areas with very permeable soils are also of concern. So we have to think a little bit in terms of the location that a field or a farm might have in the landscape. And so, going back to my earlier presentation from a few months ago, we talked about soil survey reports and how useful that information is, whether you're using the paper copies with the traditional maps, or whether you go to the online version, the so-called web soil survey, which is just a fantastic tool. It provides you with information on basic soil properties, on suitability for use, and in this case, also the environmental loss potential. So the soil survey can be a very good sort of first source of information to start thinking about these problems and how to address them. Okay, so let's look at one of the concerns that we have, and that's erosion. And there's two aspects of erosion that are undesirable. One, it removes the good soil. It removes the soil right from the surface. It's typically the soil that's the highest in organic matter, and that's the most desirable. And what it leaves behind typically is the kind of the gravelly material, the coarse fragments that don't get washed away as easily by the runoff water. So with many years of erosion, we basically lose our best soil. The other aspect, of course, is that this soil ends up somewhere else as sediment, and this pollutes water resources, whether it's streams or eventually going into lakes or estuaries or rivers. And this covers aquatic habitat. It makes it less suitable for drinking water or even navigation. So both of these aspects, of course, are highly undesirable. And erosion really remains a large problem here in the United States. We still have a lot of concerns about it. So there's a number of factors that affect that, soil type and slope. So typically soils that have a high runoff potential also have higher erosion potential. Steeper slopes, of course, are of greater concern. Soil health can be a big factor as well. If we basically build the soil up with, say, good aggregation, good plant rooting that pumps the water out very well, we are going to be reducing the erosion potential. And then also surface management, whether we keep the soil covered or whether it's exposed using tillage or herbicides or something like that, that can greatly influence the erosion potential. So here's a quick illustration of that shows these four graphs in different stages of the development of erosion. So on the top left, we see a raindrop, and a raindrop actually has a certain amount of energy, basically from its mass and its velocity. It then reaches the land surface, and that is basically what initially creates the concern. When the soil is dry, it is relatively hard and initially resilient and can absorb the energy of that raindrop. But as the soil starts to wet up, it becomes soft and it becomes weaker, and the raindrop energy cannot be absorbed quite as well, to the point where that surface layer becomes very soft and very susceptible to the energy of the raindrop, which may cause then the aggregates or the soil itself to be smashed and dispersed. And you see that here in the picture. You see the very soft soil, and you can actually see the impact of the individual raindrops that basically destroy the soil. You start to see water accumulating at the surface, and if this is on even a modest slope, you start to initiate runoff and then erosion. Now, one thing we could do is of course we could try to cover that soil with, say, mulch or some other type of say organic compound, maybe even some compost, and that material, that surface cover, can then absorb the energy of the raindrops. So instead of it falling directly onto the soil, it's being absorbed by, say, the mulch, and this greatly reduces the erosion potential. So one of the best things we can do to reduce erosion is to have the soil covered. And that's depicted here in this rather famous graph that shows the relative erosion or soil loss from 0 to 100% and the percentage surface residue. So if we have bare soil, we have losses at 100%, but we see then a fairly rapid decrease in the erosion losses, even with modest amounts of surface residue. So if we have about 30% surface residue, we reduce the erosion losses by about 60%, from 100 to 40. And then if we increase the amount of surface residue, in the end we end up with relatively low erosion losses. So one of the best things we can do in terms of reducing erosion losses is to cover the soil. And the good thing is this also has a lot of benefits in terms of building healthy soils, to reduce the effects of extreme water and temperature conditions at the surface, to promote biological activities. So to some extent it is a no-brainer to put mulch or other materials on the surface. So in terms of erosion and runoff then, what are sort of the main strategies? In summary, avoid fields that are prone to flooding or have high runoff potential, if at all possible. Keep the soil covered with mulch or residue or even compost. Build and maintain soil health, especially aggregation, to increase infiltration capacity and reduce the runoff potential. And then use grass alleyways, preferably along the contour. So there's some pictures here. This shows, of course, the surface mulch. This is also soil that has received compost, and so it's in really good shape, kind of like the soil that you see here. This is a picture that shows these alleyways that in the winter time will have a rye cover crop, and this can then be mowed onto the rows. In this case, we have grapes here in South Africa, but we can use that then as a mulch to go into the rows. Of course, you can bring in external sources of mulch as well. And then the bottom picture shows you a grass alleyway, especially if it's along the contour. That's good because it will infiltrate water quite well. It will filter out any sediment that might come from the rows if they are unprotected. So those are some good management approaches that are really not difficult to implement, and in fact are being implemented by most berry growers. Okay, so let's continue on and now talk about nutrients. In the early seminar, we discussed the 9 what we call macroelements, the elements that plants need in relatively large quantities. So the carbon, oxygen, and hydrogen are available, plentiful in the natural world, and it's primarily the nitrogen and the phosphorus that are the ones that are applied in large quantities, but are also of environmental concerns. So that's what we'll be focusing on. So this pictograph shows the difference in loss pathways between nitrogen here on the top versus phosphorus on the bottom. And although they are both nutrients, they behave very differently in the soil, and they have very different impacts. So we'll discuss those in some more detail. So nitrogen can be in the soil in both organic or inorganic form as nitrate and ammonium. Most of the nitrogen, we hope, will be taken up by the crop. I mean, that's our objective, and that promotes good growth. It may run off or erode, but typically with nitrogen, that's a relatively insignificant loss pathway. It's mostly the leaching and the volatilization and denitrification that are the primary loss pathways. And so those are the ones that we are concerned about. They are both initiated by very wet soil conditions. Now phosphorus, on the other hand, can be in the soil also in organic and mineral form. Again, the desired pathway is crop uptake. Leaching is only a problem in some very rare cases where there's just excessive amounts hugely excessive amounts of phosphorus in the soil, where we're dealing with very sandy soil with shallow water tables. But in most cases, it's really the runoff and the erosion that's a primary concern with phosphorus. So let's look at each of these in a little bit more detail, starting with phosphorus. So here's our pictograph again. So it's primarily the runoff and the erosion that's of concern. Here's a picture from a lake in Canada with a barrier in between that shows the area that received phosphorus inputs and then the area that did not. Most of the freshwater lakes in North America are phosphorus limited, and it actually takes relatively little phosphorus to induce eutrophication or algae growth or even aquatic vegetation. And this is to some extent the natural process, but it gets accelerated by phosphorus that comes from farms. Again, berry farms are probably not a huge contributor, but they could contribute with poor management practices. Well, one thing we need to keep in mind, because erosion and runoff are the primary processes for phosphorus losses, then from that, of course, it's a logical conclusion to say practices that reduce runoff and erosion also reduce phosphorus losses. And so, having surface mulch, improving infiltration capacity through good soil health management, etc. These are all practices that also reduce phosphorus losses. But there's another dimension to that, and that's basically the accumulation of phosphorus in the soil. If we end up with lots and lots of phosphorus in the soil, then we increase the loss potential, and that's an additional concern. So if we just think about phosphorus levels in terms of a soil test level, which we of course measure on a regular basis, we know that if the soil test levels are very low, that we have reductions in yield, and that there is sort of a point where you say, well, there's sufficient phosphorus in the soil for good crop production. We have sort of an optimum range. But then if we really get too much phosphorus in the soil, then we have excess, and this excess phosphorus is much more susceptible to losses through runoff and erosion, and that's a concern. So the above graph is basically kind of a hypothetical case. On the bottom here, I'm showing you some real data of relative yield. This is for corn and alfalfa and grass, but it shows you that in this case for a Morgan extractable P, that if you're sort of in this range of 4 to 6, that's sort of where the cutoff is between going from below optimum to optimum. And so you don't have any yield increase beyond that, but then at some point in time you're starting to get into excessive levels. And even though the response to soil P levels is often quite somewhat variable and low precision, there is really strong agreement that these levels, that there is a certain level where you really have an optimum amount of phosphorus in the soil, not deficient and not excessive. And so I just wanted to show you as a comparison, because many of you may be using different extractants. Here in the Northeast, we mostly use modified Morgan, which is just like Morgan, certainly in terms of phosphorus. Some of you may be using Olsen or Bray or Malic 1 or Malic 3. And this here shows the different ranges, because the extractants are slightly different, and they end up with extracting a little bit more or a little bit less phosphorus depending on the method. And so they each have their ranges in terms of low, optimum, high, and very high, and it's under the very high where we get to be concerned about excessive phosphorus losses. And so we would like to be able to prevent that from happening. We don't want to have too much phosphorus in the soil that will possibly cause environmental concerns. Now, in most cases, if a farmer regularly soil tests and is very careful about how much they apply, you don't really see any problems with that. The cases where you do see that occurring is typically with a lot of organic inputs. So we see that with manure, especially say on a dairy farm that has a lot of excess nutrients, then that builds up the phosphorus. Or we also see it sometimes with repeated compost applications, sometimes even with organic farms, because both manure and compost are not as well balanced in terms of nitrogen and phosphorus. That is that you typically apply too much phosphorus for what the crop needs if you apply the right amount of nitrogen. So you do this year after year, and then you start to build up your phosphorus levels. So these are some real soil samples of cases where there's been an increasing amount of organic phosphorus applied, and these are then for malic or for margarine, the soil test levels, and you can see that they really build up, and they are really highly excessive, which is really what we would like to prevent from happening. So if you have a situation like that, when you have too much phosphorus in the soil, then you need to make sure that you change the diet, you might say, of the soil, where you add your nitrogen in a different way. Perhaps you can do that by adding, say, clover residues or alfalfa, or if you're not an organic grower, then perhaps you can simply apply some nitrogen fertilizer and a smaller amount of compost, so that you can start reducing those phosphorus levels in the soil. So, and we account for that in the Cornell Soil Health Test in terms of the scoring curve that we use for phosphorus analysis. And that was discussed in the previous webinars by Bob Schindelbeck. So the scoring curve, basically the idea is that we interpret an actually measured value of a soil health indicator, in this case phosphorus, and we interpret that on a scale from basically 0 to 100. So if we have very low phosphorus levels, then we give it a very low score, and as the phosphorus level increased, then we increase the score as well. So, and this is then where we, around 4 to 6, where we reach the optimum level, but then we start to downscore it, basically, when we start to reach excessive levels of phosphorus. So it is important that you try to keep your phosphorus level sort of in this optimum range, so sort of between about 4 or 5 and about 20, and that you don't want to go into excessive levels. So to summarize the phosphorus management, what are the main strategies? Well, the first 4 that we see here are the same as we used for runoff and erosion prevention, okay? Because if you don't get any runoff, then you don't have any problems with losses. So the same one: avoid high flooding locations, keep the soil covered, maintain soil health, and maintain grass alleyways. But now we have this 5th consideration, is monitor the soil phosphorus levels and try to avoid excessive phosphorus. So these 5 management strategies are very effective in reducing P losses. Okay, so we've talked about erosion, we've talked about phosphorus, now let's talk about nitrogen. And nitrogen is a very kind of complex element in the soil. And both in terms of how it behaves in the soil, but also in terms of the larger considerations around nitrogen. And there's a number of concerns that we have around nitrogen these days. One is the high energy consumption that's associated with the Haber-Bosch process, that basically is the industrial process that takes atmospheric nitrogen to reactive nitrogen. It requires a lot of natural gas, a lot of energy, and it generates a lot of carbon dioxide. Secondly, we have a persisting concern about groundwater nitrate levels. We haven't really seen a lot of improvement in general over the past couple of decades in nitrate levels, which is the result of excessive nitrogen applications, especially in these more sandy areas or even urban areas. The other one that we're concerned about is the losses of nitrogen into streams and rivers and then into estuaries. And this map here on the bottom shows the about 300 locations around the world where there are a lot of concerns with high levels of nitrogen in estuaries causing hypoxia or low oxygen levels and fish kills and all that. One area that's really quite well known is northwestern Europe, where there's a lot of nitrogen use, a lot of intensive dairying. This is the original area of where the dairy systems were developed. And then, of course, in North America, the area along the East Coast, starting sort of with southern New England, going down to Florida, and then, of course, along the Gulf Coast, where we have probably the largest problem as a result of all the nitrogen that comes out of the Mississippi River Basin, primarily associated with corn production. But these are often very important estuaries, like, for example, the Peconic Bay on Long Island, where there's a lot of concerns, even from horticultural farms, about trying to reduce nitrogen losses. So the fourth area of concern is greenhouse gases, primarily nitrous oxide, N2O, which is the result of denitrification. And again, berry production may not be a huge contributor, but agriculture overall has a very large footprint in terms of greenhouse gas impact, actually very disproportionate to the share of the gross domestic product. About 7 to 8% of greenhouse gases are associated with agriculture, and most of that is nitrous oxide losses, because nitrous oxide is about 300 times more potent than carbon dioxide. And so we need to try to reduce that through prudent and judicious nitrogen management. So let's go to our pictograph here about nitrogen. Again, crop uptake is desirable. We may have a little runoff and erosion, but most of the losses will be leaching or denitrification. If we have a more sandy, gravelly soil, most of it will be through leaching, and this is as nitrate, because nitrate is negatively charged, and the soil is negatively charged as well, so therefore it very easily percolates down and washes down with the water in the soil. The volatilization and denitrification losses are primarily N2, which is the nitrogen gas that's also in the atmosphere, which is not at all a concern, because 78% of the atmosphere is already dinitrogen gas, but it's the nitrous oxide that's the primary concern. Now, when we have a denitrification event from, say, a heavy rain, we may actually lose quite a bit of nitrogen. We may easily lose 30-40 pounds of nitrogen per acre, either through denitrification or through leaching with a heavy rainfall event of, say, 1.5 inches. The other component that I should mention is volatilization of ammonia. That is also a concern primarily with acidification. So the nitrogen cycle, of course, is relatively complex, and I won't go into detail about that. I think the main point is that there's a lot of these transformations that occur in the soil that are in part driven by all these sources of nitrogen that come, from agriculture. And when it moves from one state to the other state, it may become subject to leaching or denitrification and gaseous losses and all that. So I'm going to simplify that by using this graph here. So this first shows the sources of soil nitrogen. One of them is we get a little bit of nitrogen from the atmosphere, typically about maybe 6 or 8 pounds per acre. It's free nitrogen basically, but a relatively small quantity. In most field conditions, we get a significant amount of the nitrogen from the mineralization, or basically the decomposition of soil organic matter that may be native in the soil, other organic materials that may have been applied, like manure or compost or residues, and then cover crops, especially leguminous cover crops like clover or alfalfa. And these all get decomposed, and the organic nitrogen is mineralized to inorganic nitrogen, primarily as a result of biological processes, which are in turn affected by temperature. The other source of nitrogen, of course, is mineral nitrogen, which is fertilizer. It could be ammonia type fertilizers. It could be nitrate type fertilizers. So we have all these different sources of variation that are associated with nitrogen availability, and that makes it actually a little bit more difficult to manage nitrogen. Different soil types have different sources. If you're looking at the Midwestern soil, they have a lot of organic matter, and it's very deep, and they have good structure. They provide a lot more nitrogen than, say, a soil in the Northeast that's very sandy, and a pot soil type soil that has relatively little organic matter and nitrogen mineralization. Of course, the amount of organic matter in the soil affects the nitrogen availability, and we have seen soils build up organic matter when they're very well managed, or lose organic matter when they are, say, have a history of intensive tillage or erosion. Of course, how much you add in addition in terms of organic amendments like compost and manure, whether you have cover crops and what types of cover crops, leguminous versus grass cover crops, for example. Soil and crop management, how intensively you till and things like that. Whether you have drainage or not, and if you have poor drainage, then you may get a lot of losses, especially of nitrogen. Temperature is a factor, because a lot of the mineralization is temperature mediated, because it's a biological process. And then, of course, last but not least, precipitation, because a soil that's, say, very dry will not mineralize nitrogen, or soil that's too wet won't mineralize nitrogen. And all these things, in a way, interact in very complex ways, and that's what makes it very difficult to precisely predict how much nitrogen needs to be added to your soil to adequately feed the crop. But there are really some guidelines that we have if we understand the system a little bit better. So this picture here shows the nitrogen mineralization as part of the incubation time. This is from an earlier paper by Kasman and Munz. And what it shows you here, that most of the nitrogen comes from the surface soil. This is the 0 to 18 centimeters, which is about 0 to 7 inches. And we see an increasing amount of nitrogen being mineralized over incubation time up to 100 days. This is the square root, so it's 100 days. And then we see that as we go deeper into the soil, less and less nitrogen is mineralized and becomes available. So it's the surface soil that's the most important, that provides the majority of the nitrogen. So in the field, and this is a laboratory study, but in the field, nitrogen release will be affected by weather conditions like temperature, soil organic matter content, soil types, etc. So let's now consider the losses. So we looked at the sources of N, and these are the primary losses. One of them is ammonia volatilization, and that can be the result of the application of ammonia type fertilizers, especially if they're left right at the soil surface, so that they can volatilize. You can reduce that by basically incorporating it or injecting it into the soil. Also, manure can often have ammonia fertilization, so if you apply manure or even some compost and you leave it on the surface, then you might lose some of that through volatilization. We talked a little bit about runoff and erosion. Tends to be not that big of a problem. The primary losses of nitrogen from runoff and erosion is when you leave the organic or inorganic fertilizer on the surface and it gets removed in a heavy rainfall event. The other losses, the major losses, are denitrification and nitrate leaching, as we mentioned. Again, the primary objective, of course, remains getting the nitrogen into the crop. So again, it's management, soil health, precipitation, and temperature that are all critical factors. In terms of the losses, it's always, if you get a lot of water, you get a lot of precipitation, that creates most of the problems. That can create the leaching. Denitrification is affected by both precipitation and by temperature, because it's an indirect loss and it's a biologically mediated loss. So if you have actually very cold soil, you may have quite a bit of nitrogen in that soil, but you won't get much denitrification losses because the soil is cold and the biological activity is low. So when you really do see a lot of denitrification losses is sort of a little bit further into the growing season, when the soil has become warm and then you get a lot of rain, and you can lose easily 30 to 50 pounds per acre in a heavy rainfall event. And so in a way you'd like to be able to account for that. So when we go back to our basic properties in terms of pore sizes, we can think of the loss potential again in terms of large pores, good aeration, so it reduces denitrification losses. Small pores reduces leaching losses. And ideally you have some of both, because that provides a well-balanced soil, which you tend to get from a well-aggregated soil. Another concern related to nitrogen is poor internal drainage. So if you have barriers deep in the soil and you have water tables that are at relatively shallow depths, that promotes, of course, denitrification losses. You can remediate that through installation of subsurface drain lines, and of course raised beds also reduces susceptibility to imperfect drainage. So it's a component that's often forgotten, but poor drainage creates problems, especially with nitrogen losses, but even with runoff and erosion and phosphorus losses, because soils that have poor drainage tend to have higher potential for runoff because the soil remains wet and saturated. So what are the main strategies then for reducing nitrogen losses? Do not over-apply nitrogen by accounting for all sources of nitrogen inputs, like the soil organic matter, compost, manure, fertilizer, etc. Ideally provide nitrogen in multiple applications and account for weather factors. We're actually on the scientific front making a lot of progress in this area. We now have for field corn and sweet corn, we have a tool that we developed, the Adapt-N tool, that allows for prediction of how much nitrogen you need using model simulations, accounting for all these weather effects that we discussed. But I think even for berry producers where we may not have a tool like that, you can have basic rules of thumb. If you have, say, a very wet spring, then you probably lost some of that nitrogen through denitrification and leaching, depending on your soil type, and you may need to make up for that and apply a little bit of extra nitrogen, say, in your second application. But if you have a relatively dry spring, you may want to do the opposite because you didn't have any losses, so you don't want to over-apply. So you can even, without really using sophisticated methods, you can make some adjustments to your nitrogen based on the weather conditions. Next one, build and maintain soil health, aggregation, organic matter, etc. That, especially on the medium to fine textured soils, will help with aeration and with water and nutrient retention. So soil health management, again, it's important not only from a production perspective, but also in terms of reducing the environmental losses. And then finally, as I mentioned, facilitate good drainage. So I wanted to show you these two soil health reports, and to look at that sort of in the context of the environmental loss potential. So these are two very similar soils, but one had a history of no manure inputs, and the other one had a history with manure inputs. And even though these soils inherently are very similar, they're medium textured soils, you can see that the aggregate stability without manure was 53%, but it became 78% with multiple manure inputs. So we have actually made the soil more desirable by allowing for better aeration, reduced potential for denitrification losses. The available water capacity went from 0.1 to 0.26, so we've increased the ability of the soil to retain the nutrients as well. So we've both reduced the denitrification losses in principle, and we've reduced the leaching losses because we have better water and nutrient retention. Also notice that the organic matter content without manure was 2.6, and with manure it's been built up to over 6%. So that has a lot of benefits. Similar with the active carbon and potentially mineralizable nitrogen, that's an indicator of the amount of nitrogen that we can expect from mineralization. That went from about 6 to about 23. And so this soil on the right, of course, can provide a lot more nitrogen from natural sources than the one on the left. So all in all, the one on the right with the manure inputs is of higher health, higher quality, and presumably reduced environmental impacts. Okay, so this is then my last slide where I want to put everything together that we've discussed in the past hour. And I think first and foremost, most berry production systems have low environmental impacts from nutrients and sediments, and part of that is because that is inherent with the production practice and the fact that you're using a perennial plant, so there's not a lot of tillage going on. There's not very large amounts of nutrients that normally get applied, and so it's not as big of a concern as perhaps corn production or some of these other major crops. Site characteristics like soil type, location, etc. can affect potential losses, like for example when you're on a floodplain or whether you have very clayey soils and naturally soils that have high runoff and erosion potential. In addition to that, through management, we can increase or decrease the potential for these losses, leaching or runoff and erosion. So when we build up the soil, through good soil health management, we can increase productivity and reduce the environmental impact. So it's a win-win situation. And then, in addition, we need to make sure that we don't put too many nutrients out there, that we are careful about what we apply. So prudent nutrient management can prevent most of these losses. And with that, I will hand it over or back to Laura, to our moderator, and be happy to entertain questions.
Thank you, Harold. I know that Tom has a question about whether or not the soil health test that you showed, second to the last slide, was with manure from a corn silage field. And then I actually had some questions about that same slide. So I don't know, would it be possible to go back to that?
Yes, we can go back to that. Yes, I mean the soil on the right, they were both soils that were in corn production, and the one on the left was primarily corn for grain, and the one on the right was part of a dairy system, so it was corn silage with manure inputs.
Okay. Hopefully that answers Tom's question, and my question may be a little bit off topic from the berry example, but I'm just wondering about the root health rating. I struggle a little bit with the soil health test trying to understand what's happening, and definitely I can see the positive impact that manure has, but why is the root health rating lower, do you think?
I would have to go back to all the details about the particular farm, which I don't really have with me. It probably has to do with the fact that the field that received the manure inputs also had rotations with alfalfa, and we used the bean bioassay to look at the. So let me just put the arrow there. We use a bean bioassay, so which is also a legume. So we may have increased the root disease pressure a little bit simply by the rotation. It's typically the rotation and the types of crops that are part of the rotation that are the primary concern. But keep in mind that we use for the root health rating, we use a sensitive indicator crop, which is snap bean, basically. And that's what we use in comparison. Now, if you're not growing snap beans, of course, then you need to understand that your crop might have slightly different susceptibility. But we selected snap bean because it is the best indicator typically that you can use for vegetable production.
Okay, great. Thank you. It looks like there's a couple of other folks typing, and maybe we can get some other questions here. Kathy wonders, how long does the effect of a heavy downpour persist in terms of nitrogen losses to soil? Is it an hour or so after the event, or a day or more?
Okay, good question, Kathy. Yeah, so if you it takes a little bit longer. It takes several days. When we have a more finer textured soils, like a silt loam down to a clay loam, when we get a lot of rainfall, the soil becomes saturated, and if it doesn't drain well, then the soil remains saturated. And then it takes about 2 days. In fact, we've done a lot of research on that and taken a lot of measurements. It takes about 48 to 72 hours then for these anaerobic conditions to occur, and that's when you get most of the losses. So it's not immediate, because the soil needs to remain saturated for about 2 days for the EH, or the redox potential, to go down, and that's when you get most of the losses. And similarly with leaching losses, it takes about a day or so, a day or two, for the water to move down through the soil and then to wash out most of the nitrogen. I hope that answers your question.
Okay, great. And then there is another question from Glenn. He's wondering if the additional traffic from manure applications increased the surface and subsurface hardness. I think he's referring to that very slide that.
Right. Yes, absolutely. And we do see this a lot on dairy farms, where the soil health indicators are all looking great. It's all in the green, and the ratings are very high in the 90s. And then we see that the hardness is typically, the soil is very hard, and so the score is very low on that. And that's because on these fields that receive manure, a lot of the manure gets applied with very heavy manure spreaders, oftentimes under very marginal conditions. The farmers want to get the manure onto the land early in the season because they want to get to planting, and so a lot of these soils actually show a lot of compaction problems. Yeah, that's very observant of you.
And then again from Glenn, he's wondering if there's relationships between temperature and precipitation have been condensed into interpretive rules by which one could apply observed and forecasted weather data into adapt-N recommendations.
Let's see. Now I need to look at that really quickly myself, shouldn't I? I've been condensed into interpretive forecast. Yes. So if you're interested in adapt-N, I would encourage you to just go to our website. If you just Google adapt-N, you will get there. But the adapt-N system is basically it involves a dynamic simulation model which simulates soil and crop processes like water movement through the soil and nitrogen transformation, and it also accesses a high-resolution weather database that was developed here at the Northeast Climate Center, right here in the same building where I am now, Bradfield Hall. And so the adapt-N tool basically simulates all these conditions for the early part of the growing season. It estimates the nitrogen additions through mineralization and all that, and it estimates the losses, and then it comes up with a recommendation for site dressing, in this case corn. In principle, we could also get into other crops. But that's what it does. It's very dynamic, and it takes all of those temperature and precipitation factors into account, and it does it in a kind of a daily time step.
Okay, and then there's a question from Tom. He's wondering if there's any new research on remediating compaction, mechanical ripping, or biodrilling with a deep-rooted crop like forage radish or alfalfa.
Well, yeah, Tom. Those are, of course, some of the things that more recently have been developed. I think The bio drilling is very exciting. This is for those of you who are not familiar with it. Ray Weil at the University of Maryland has done a lot of work on that, often in collaboration with Steve Groff, who is a very progressive farmer in southeastern Pennsylvania. The idea is to use radishes, especially. You can plant them in September, typically, for most of the areas that we're concerned of, and they establish very strong and fat roots. I mean, they're radishes, and that basically kind of loosens up the soil. We call that bio drilling. So if you have compaction, the best way to address that is to find some way to decompact, and it could be through biodrilling. It could also be simply through some limited and targeted tillage, and then to try to prevent that from happening through soil health management practices and organic matter additions and all that. The soil becomes more resilient to compaction and more resistant if you have better aggregation and better air exchange and all those kind of things. Yeah, so those are some of the areas. We've talked in the past about using frost tillage as well. That wouldn't be that appropriate for berry production, but it's you basically till the soil when it has a very shallow frozen surface, and that can be if there's been a lot of compaction that occurred in the fall, that can be a way to alleviate the compaction that way. And you do that at particular time windows during the winter.
Okay, and then Kathy has two related questions. She's wondering if there is then a short-term and/or long-term residual effect on nitrogen availability after the heavy rain event. She's going back to that question initially that she asked. And then if nitrogen is applied after the heavy rain event, is it more susceptible to loss if another event follows?
There's not necessarily a residual effect that I'm aware of, and so if you have such a heavy rainfall event, you lose a certain amount of the nitrogen. So if most of the nitrogen that's in the soil is in the nitrate form, so the most reactive form, then you will lose a significant amount of that with a big rainfall event, either through leaching or through denitrification. And then it's gone, and you won't get it back, basically. Then there's necessarily not a residual effect per se, other than that the soil is, at that point in time, quite wet. So if you get another rainfall event, say 4 days later, and the soil is already wet, then of course you can go into another leaching or denitrification event. But if you apply the nitrogen, subsequent to these events, and not immediately, but say, a week later or something like that, then in principle that's not being impacted by what happened to the previous nitrogen, and that is a way to make up for some of these losses.
All right. I think. Does anyone else have any questions for Dr. Van Ness? All right, they're pretty quiet. I'll just move into the exit screen. I want to thank Dr. Harold Van Ness for being with us today. And I want to remind the group that remains that the speaker for the next webinar is Dr. Belinsky Santos, who is the Assistant Professor of Horticulture at the University of Florida. And the topic will be fertigation and hydroponics of strawberries. He'll talk about new diagnostic tools and precision agriculture for berry crops. Again, if you have not completed the demographics questionnaire or the pretest, please take an opportunity to do that right now. And I want to thank all of you for joining us, and we will see you. The next webinar is March 2nd, so we have a couple of weeks break, and then we'll be back on March 2nd and March 9th, finishing again with Dr. Van Ness. And thank you.